Okay, so we've got the right-hand rules and we have chapter 24 review taken care of. Any questions about chapter 24 now that you know we have recording going and everything? No? Excellent. Chapter 22 is where we learned about magnetism. So make sure that you know the difference in ferromagnetism, the strong magnetism, that when you put something that's ferromagnetic in a strong magnetic field, it's going to have a strong attraction. So ferromagnetic material, put in a magnetic field, it'll have strong attraction. Paramagnetism is the same as ferromagnetism, but weak. And then diamagnetism is weak but repulsive. So if you take something that's diamagnetic and you put a strong magnetic field, you have a weak repulsion. Everything has diamagnetism, but it's so weak that if it's paramagnetic or ferromagnetic, you don't observe the diamagnetism. And so we talked about in class things like levitating a frog because water is diamagnetic and frogs are largely water. Magnetic charges come in only two types, north and south. But more importantly than that, they always come as one unit. You have north and south. You can't get north by itself or south by itself. Theoretically, it could be possible, but it's never been observed. So for a class like this, we will simply stick with it doesn't happen. So you always have a net magnetic charge of 0. Right? With electricity, we can have a net negative charge or a net positive charge. Magnetism, because it always comes with equal north and south, you always have a net magnetic charge of 0. You have rules for the forces, just like we had with electric charge, that opposites attract and likes repel. And then we have the obscure thing that we named the charges north and south, with north being short for north seeking. So a north magnetic pole means that it seeks the Earth's north geographic pole. But because opposites attract, that means that Earth's north magnetic pole that's being sought must be a south, or north geographic pole must be a south magnetic pole. So the north pole is the south magnetic pole, is the outcome of the way they named it. Peyers Law. Peyers Law is the law that goes with that second right-hand rule picture. Peyers Law says that if I have a current going through a wire, it's going to create a magnetic field. I'm not going to put the vector sign here. I put sum of B dot delta L. You have to make a loop around your current. So in the case of a wire, we make a circular loop. The magnetic field, there's a dot in that, so that means the dot magnetic field that's parallel. Got to have a vector sign over the L, or it means just multiplication. The magnetic field is parallel to the length, sum going around the circle. Because of my symmetry, that's just magnetic field times the circumference, times 2 pi r, is equal to mu naught, the permeability of free space, times the current. Basic outcome is B for a straight wire is mu naught I over the circumference of the circle, 2 pi r. So, what are you going to have using Ampere's law? If you're in the calculus-based class, you might actually have to do a calculation with it and say, okay, so we're going to use a circular path because then B is parallel to DL anywhere on it, and show the calculation. If you're in the physics 152, which most of you are, then you would say, I'm this far away from the wire. What's the magnetic field? You're given that equation, but it comes from Ampere's law. So you don't have to specifically cite Ampere's law then. So the only place you really have to cite Ampere's law is to say that a flowing current produces a magnetic field. That's the only real outcome that you have to know on the test from Ampere's law, because you'll have the equation that comes from this. We also applied Ampere's law to a coil to find the strength of the magnetic field inside the coil. We went through the derivation in class. You'll be given that equation on the test, so you don't have to be able to go through the derivation. But once again, that's saying that the current created the magnetic field. So that's the importance of Peyers Law. I usually say it the American way of Peyers Law, but trying to be a little more correct, especially because a certain student is giving me grief about pronouncing my French words incorrectly. I think I've already talked about these rules. Magnetic forces opposite to attract likes repel. If you have a charge moving in a magnetic field, well, that's where we had to use the right-hand rule number 1 for a cross product. A charge moving in a magnetic field had force is equal to Q V cross B. So you do that right-hand rule with V cross B, and then you take that answer and multiply it by Q. So if V cross B points, for instance, north, then if I multiply it by Q, if Q is positive, my answer is north. If Q is negative, my answer is in the negative north direction, which we typically call south. So you have to remember that the force direction will be reversed from what you got with the right-hand rule if the charge is negative, because you're multiplying by a negative value. Then we had, what if it's a wire carrying current instead of a single charge moving? In that case, it was, wow, that's not a nice looking F. Force is equal to IL cross B. So again, use the right-hand rule to find the direction. Now remember, anytime you do a cross product, the magnitude is IL, oops, that's not an L, ILB times sine of the angle between the two vectors. So L and B were my vectors, so it's going to be sine of the angle between L and B. And likewise with my equation for a moving charge, I would have had and what would the angle be in this black equation for the moving charge? Angle between what and what? The angle between V and B, the two vectors that were in the cross product. So that's these two. Force between two current carrying wires. I define the force between two current carrying wires. It's a two-step process. Step number 1, find the magnetic field of wire 2 created by the current in wire 1. Once you found the magnetic field at wire 2, then you can use the red equation here to find the force on wire 2 due to the magnetic field created by wire 1. So you're going to have to combine, where is it? That equation in black there to get how strong the magnetic field will be at wire 2 due to the current in wire 1. So you have B1 is equal to mu naught I1 over 2 pi separation between the wires. Let's call it D just to make life easy. So that's what your B is going to be. And then you have I2 is going to be the I in the red equation. So you have I2 times the length of your wires. We usually calculate the force per length because you know what your length is in this problem, infinity. Right? Our equation only works for the magnetic field if it's an infinitely long wire. So we do force per length is equal to I2 times mu naught I1 over 2 pi separation. So then the question comes, if I have parallel wires, are they attracted or repelled from each other? That is parallel wires with current going the same direction. So if I have two currents going up, are they going to be attracted or repelled? Okay, I got two people said attracted. I don't have it memorized. I'm guessing either you did or you're faster than me in your mental math here. But what I do is I say, okay, this wire here is making a magnetic field that's going this direction at this wire. And so then my force is equal to IL, so my L is up, cross B, and it's going back toward wire 1, so attracted. You guys were right. But that's how you actually determine it, by using the right-hand rule with that process of finding the magnetic field created by wire 1. Okay, that required right-hand rule number 2. and then the force between a current carrying wire and a magnetic field, which goes back to right-hand rule number 1. Right hand, there's a reason Lydia had a nightmare about the right-hand rule, right? It comes up all over the place here. Electric motors. Fundamentally, why does an electric motor work?
Because of the torque.
Okay, you create a torque when you have
charge running through it.
Current passing through the coil.
Okay, these are true things, not the answer I was looking for. You create a torque when you have a magnetic field and another magnetic field that are not parallel. Because there's always going to be a torque to try to make them align. And we calculated that torque by actually taking a coil. We made a rectangular coil, so our calculations would be easy, but the calculation works for any shape. And we calculated the torque on each side of that due to the current passing through a magnetic field. And then we added it all up. That was our net torque. And it turned out that for an electric motor, the peak torque is N, the number of turns, times B, the magnetic field strength that's external, times A, the area of the coil. So it doesn't matter if it's a rectangular coil or a circular coil. Times the current. It's like there's one more thing. So the torque max was equal to INBA. This is the maximum torque you can have for an electric motor. But as it rotates, the angle between the magnetic field and your area is going to change. And that's going to change the torque. And so the torque at any time is INBA sine of theta, where theta is the angle between the area of my loop. Now keep in mind, the area is in the direction normal to the loop. So if my loop was drawn on this table, the area would be coming up out of the table. So it's the sine of the angle between that and the magnetic field. So that's the torque at any orientation, as well as the maximum torque. This is a much longer review than I had intended when I started class.
It's a lot of stuff in these chapters.
It is. Yeah, I was talking to Nathan. Yeah, it's only 3 chapters, and the last one's really short. The other 2, not so much. So chapter 23, magnetic induction. This is where we have electromagnetism, so to speak. When we start saying the magnetic field is going to cause electric behavior. And so we started with Faraday's law of induction, which says a changing magnetic flux induces an electric voltage. So we had E, which is the voltage, equals minus N change in magnetic flux over change in time. Well, in that is built in that you have to know what magnetic flux is. B dot A, magnetic field dotted with area. That means you're taking the direction of the magnetic field times the direction, or excuse me, the strength of the magnetic field times the area of your loop, whatever shape is, times the cosine of the angle between the area and the magnetic field. Why cosine? Because it's a dot product. Dot products are multiplying parallel parts. So that means identical to equals BA cosine of the angle between them. So if you have a magnetic field strength that's changing with time, it's going to have a changing flux and it's going to induce a voltage. If you have an area that's changing in time, it's going to create a flux that induces a voltage. Or if the angle between the area of your loop and your magnetic field is changing, it's also going to change the flux and thus create a voltage. So any one of those things changing, the B, the A, or theta, if those change, it's going to create a voltage. And of course, if theta is changing, well, calculus students know how to take the derivative of cosine omega t. people not in calculus don't know how to do that, right? So if you have a constantly rotating coil in an extramagnetic field, then you're going to have minus NBA omega, sine of omega t. So people without calculus, you just jump straight to that equation. If it's rotating at a constant rate, omega, remember omega is units of radians per second, with omega is 2 pi f, where f is cycles per second, then that is what you have for the induced EMF. What's the point of this minus sign? I mean, it's there for mathematical reasons, but for you and me, I said its point is to remind us to look at Lenz's law to get direction. Lenz's law says that the induced EMF, the voltage produced, is going to be in the direction to make a current flow that will oppose the changing flux. So if flux is increasing, then the induced current is going to try to make a magnetic field that would keep it from increasing. If the magnetic flux is decreasing, then the induced current is going to try to supplement it to keep it where it was. So that's Lenz's law. You can't have any useful Faraday's law of induction without having Lenz's law as well. Eddy currents, remember we had the cool little demonstration of dropping a magnet through a tube. And eddy currents are loops of current created by the changing magnetic flux as the magnet moves. And then the force was repulsive between the moving magnet and the eddy currents, well, repulsive in the front, attractive in the back, so that it slowed it down. I talked about its applications in things like roller coasters to give you a natural break. A generator, an electric generator, is fundamentally the same as eddy currents. Electric generators, you use a changing magnetic flux to induce a current, and that's what you're using, that induced current. So electric generator, or that induced current, the induced voltage, whichever way you want to look at it. So electric generators, you build an electric generator just like an electric motor. It's just that instead of connecting to a battery to make it run, you're connecting it to something else to draw the energy out. Hall effect, let's just not put the Hall effect on the exam. It's a good, important thing, but it'd be more confusion to remind you of it now than to take it off the test, and just the Hall effect is an application of the rules we've already learned. Inductors, transformers, they're definitely more than meets the eye, right? The point of a transformer, also known as a mutual inductor, is you have one coil of wires that creates a magnetic field. And you have a separate coil of wires that magnetic field goes through. If the magnetic field created by the first coil changes, then that's going to induce a voltage in the second coil. And so you have a linkage between the first coil and the second coil that is through magnetic field, not through direct contact. So you're going to have two separate circuits. There's no connection between the two circuits. But you have, for that mutual inductor, the transformer, the voltage in the primary divided by the voltage in the secondary is equal to the number of turns in the primary. And remember, when I say number of turns, I mean the number of loops going around divided by the number of turns in the secondary. And if, this is if, there is no energy lost, then that's equal to the current in the secondary over the current in the primary. A very important reason for transformers is if we can raise the voltage really high through our transmission wires, we'll lose much less energy in the wires. So that's why we have high voltage lines going around the country. So we have less energy loss as the electricity travels. Another important thing is to be able to separate the transformers used to raise the voltage up. I should have specified that. Right? You generate the voltage at, say, 240 volts, and then you raise it to 350,000 volts by using a transformer and just having the appropriate number of turns. And then when you get to the usage sign, you use a transformer to bring it back down. This would not work if we just used DC electricity. Why would it not work with DC electricity? There's no changing, and transformers work because of the changing magnetic flux. So if you just connect to DC, there's no change, nothing. So you can't take a 9-volt battery, connect it to a transformer, and get out 12 volts because it's DC. Self-inductors, otherwise known as inductors, they have their units of henries. And the self-inductor is you have a coil, you put current in, but when you put current in, it builds a magnetic field. But the magnetic field builds is the word I was looking for. If the magnetic field builds, then that means you're going to have, by Faraday's law of induction, an induced voltage. And that induced voltage then is, well, we call it a back EMF if we don't want it. Or if we're using it as a part of a circuit, well, that's the voltage drop across the inductor. And so for the inductor, we had the voltage across the inductor is equal to I X sub L, where X sub L was equal to omega L. And so the X sub L, we call that the reactance. The inductor isn't absorbing energy. It's just responding. Storing energy, giving it back. Storing energy, giving it back. So we don't call it a resistor because resistors absorb energy. It's just responding, so it's reacting. X sub L is the reactance. So we have something that looks just like Ohm's law there. Now that was for an inductor. For a capacitor, that's too similar in color. For a capacitor, voltage drop across the capacitor is equal to I X sub C, excuse me, where X sub C is equal to 1 over omega C. So higher frequency, you're going to have a bigger induced voltage for an inductor, but a smaller induced voltage for a capacitor. So they respond differently. As frequency approaches infinity, the capacitor just behaves kind of like a wire, whereas the inductor is an infinite resistor. If frequency approaches 0, it's just the reverse. The capacitor is 2 separate plates, no connection, resistance, it's like infinite, whereas the inductor is like a wire. And so you, in lab, made phasor diagrams. We dealt with the phase difference because the inductor and capacitor storing energy. It turns out that the phase for the voltage across the inductor, the voltage across the capacitor, is 90 degrees different than the phase of the current going through them. And we had the Eli the Iceman. The and man aren't important here. Voltage in an inductor leads the current, whereas current in a capacitor leads the voltage. That's what Eli the Iceman has to tell you. In your phasor diagrams, that was simple. The voltage across the inductor, you put it plus 9 degrees. Voltage across the resistor, you put it 9 degrees because the resistor is always in phase. And the voltage across, did I say capacitor first? Should have been inductor first, no matter what I said. Inductor was at plus 9 degrees. Resistor was horizontal, and then capacitor was minus 9 degrees. And so you should be able to calculate the reactance for an inductor, for capacitor, the total impedance that you get by using the Pythagorean theorem. Oh my goodness. Look at the time. I just did. And the current. That was way longer than I anticipated. There's probably still questions you have. Ask away.
I know this one only applies to a couple of us, but will we be doing calculus review tomorrow at all?
We will. We did calculus review, but just like today, we'll review again. Mira.
Just a question, because of the test tomorrow, is there going to be a homework assignment due Wednesday? I know there's a reading quiz.
That reminds me, was there a reading quiz due today?
Yes.
I meant to postpone that, and I never got around to it. Did anyone not do it? Nathan, because I told him he didn't have to because I was going to postpone it. I just didn't get around to doing it. So I will postpone it. I will shuttle down other reading quizzes as well. So, of course, you only see one at this point.
So if we did that one,
Then you won't have one due for Wednesday. That's right. That was your question?
well, my question was, is there a homework?
Oh, homework.
Yeah.
Expert. I can't have a homework assignment due on today's lecture because I didn't cover anything today. So if there's one that shows due today, I'm going to move that to Wednesday because I didn't cover anything today.
There's not one today.
There's not one today?
There's not one due today.
The original plan was the reading quiz today, and that was it.
I'll have to look at what is scheduled already before I give a specific answer to that because I don't want to speak incorrectly.
For Wednesday, nothing.
If you did the reading quiz that was shown for today, you won't have to do a reading quiz. And I will have to look and make sure on what the homework is. Like if there was no homework that was due on Friday because I moved it to Monday, I don't know. I'll have to look.
Okay.
Right? I don't have enough knowledge to speak. Trace.
This is a reminder and a reminder to you. Scrapbook's due tonight, but I don't know if you have the date set correctly. I don't know.
Okay. I don't know if I have either, so I appreciate the reminder. Also, I realized, what was it? Saturday night, Nathan was working on a scrapbook, and I realized I thought I was totally up to date in grading except for the first lab, which frankly I'm just going to give you all 100% on. I just haven't entered it. I know that's not going to bother you, right?
No.
And then I realized I haven't graded the first scrapbook yet. So that I will work on grading this afternoon unless something else gets in the way. And the scrapbook should be due tonight, yes. And so, I mean, for all I know, I might not have it on Google yet. I will have to check. I appreciate the reminder. Any other questions? Okay. Let's look at total internal reflection. Now, I'm not sure if you had homework that already had to be turned in with total internal reflection or not. I know that it was at least assigned. It's just not if you had to turn it in yet or not. Total internal reflection is something that we actually already have observed with the prism, and I talked about it. But I don't recall doing the equation. Did I do the equation for it in class? Okay, so we've already observed it. It's not something brand new, but we had a rule that said when light goes from faster to slower medium, and remember the index of refraction is telling us about the speed of light. So faster means that it's a smaller number. So that means N2 is bigger than N1. Then light refracts or bends toward normal. So this picture shows light going from water into air. That's going from bigger N to smaller N. But light works the same forward and backward. So all I have to do is reverse the arrows and say, okay, here light's coming in a faster medium, goes to a slower medium, and instead of going straight, it deviated toward the normal. But light works the same forward and backward. So I could take this statement and I could reverse the words faster and slower, which would be reversing this, right? And then instead of going towards, it's going to be away. So if you look at that same one that I drew here, with the arrow as it's going, straight would have been like this, but it deviated away from normal. But that brings a problem. That brings a problem because you then get to the situation where the light here's the straight, and according to Snell's law, it would deviate so it's going straight horizontal to the surface. That in itself isn't a problem. That's what we call the critical angle. It's the divisor between no problem and problem. If your angle of incidence, remember the angle of incidence is measured between normal and the incident ray, is bigger than that, then Snell's law would say so if I want to solve this for theta 2, I have theta 2 is equal to inverse sine of n1 over n2 sine theta 1. Well, let's say sine theta 1 is 0.9 and n1 over n2 comes out to be 2. Well, 2 times 0.9 is 1.8. What's the inverse sine of 1.8? Don't worry about pulling out the calculator. It's not going to help you. It doesn't exist.
Because it's bigger than 1.
Because it's bigger than 1. That's why we have a problem. The critical angle is thus defined as the angle that gives you 90 degrees. And so if I make this theta c, then this theta 2 is 90 degrees. Or actually, I did that backward. I may have done it backward, I may not have. I have to be careful on which way I do it. But so I'm just going to erase it so it's not potentially backward because I didn't think about it. So here's the way to do it right. Oh, well, you better go. The way to do it right is to just put theta c on one side and 90 degrees on the other side.